Okay, so now what we're going to do is we're going to show that the Balcom's complement language is context-free. And to do that, we're going to design a PDA that accepts Balcom's complement because it's a bit easier than context-free grammar. And to do that, though, we're going to start by listing what the conditions for a string to be in Balcom's, in the vanilla Balcom's. And then we're going to show that, well, for a string not to be in Balcom's, it shouldn't satisfy at least one of those conditions. Okay, and so remember the reason why we're doing that is because if we can show that Balcom's complement is context-free, then through this sort of long-winded procedure, we can then decide the not halting problem, which is impossible because it's undecidable. And so many students, I think, in the actual in-person lecture found that this was a bit of a drag. I also thought it was quite painful. I'm going to try to make it less painful in the lecture recording. And really, I think I want to premise this by saying that this is actually a pretty good review of regular languages and context-free languages, because we're also going to talk about regular languages here. So even if you don't really care about the details of proving this, it's actually a pretty good review to sort of refresh your memory of what a regular language is and what the computational models of a regular language is, and the same thing for context-free languages. Okay, good. And so to do this being showing that, come on, oh boy, to show that Balcom's complement is context-free, what we will first do is we will first write the conditions. Whoops, my bad. We will first write the conditions for a string alpha in delta star to be in the Balcom's, so the original uncomplemented Balcom's, because then we're going to see that, well, for a string not to be in Balcom's, it can't respect at least one of those conditions. So really, we're just going to take the complements of each of those conditions. Right, so remember, for a string to be in Balcom's, that string has to be a string that looks like the following, right? Where this is a string over delta. Delta is the union of Q, gamma, and the hash. And each of these strings are instantaneous configurations. This first one is the starting instantaneous configuration. This last one is the halting instantaneous configuration, so either an accept or reject. And the consecutive sequences of alphas have to follow the rules of the transition function of n. Okay. And so really what we're going to do is we're going to sort of split all those into more atomic conditions, and then we're just going to intersect them all together to get the original Balcom's. And you'll see why we're doing that, because then it ends up being easier to see what the complement is. Okay. So the first condition for a string to be in Balcom's, the condition C1, is, well, that string should look like a string that looks like this, right? That's the first condition. It should just have this form, right? So alpha is a string of the form a hash and then alpha 0. So really, I'm just rewriting this all the way to alpha n. But now what I'd like to add to this is that each of these alpha i's are really in Q union gamma whole star, right? So they don't contain a hash. Okay. And so this is an atomic condition, right? So it doesn't capture the whole essence of what it means for a string to be a valid computation history, because namely, this condition would also allow, just a sequence of hashes, right? Because alpha I could be the empty string. But that's okay, because when we intersect it, we're going to get through all the intersections the actual proper definition of a string being a valid computation history. Okay. But what I'd like you to draw your attention to is the fact that, well, if we just have this condition as is, we can actually model this with a regular expression, right? So this can be modeled via a regular expression. So how can we do this? Well, we can create the regular expression that describes this string, right? This string over Q union gamma whole star. So that's, let's just call that alpha rex. So, suppose that Q is, I don't know, S, QA, QR, and gamma is the dash, the blank, A and B. Then alpha rex will need to be, S or QA or QR, or the dash or the blank, or A or B. Right? So this is just saying that it's a string over Q union gamma. Of course, this first condition doesn't cover everything. So you could have something that's not a valid instantaneous configuration. You could have a bunch of S's, right? And that would be good. But to actually just describe this condition, right? And so to describe strings over this language, you just need alpha rex equal to this whole star, right? And then the regular expression for condition 1, so RC1 is just, well, the hash. Then you need a first, so let's suppose that you need a first alpha 0, so you need alpha rex. And you also need a halting instantaneous configuration, so you need a final alpha rex here, which ends with a hash. And then in between, you can have any number, right? You can have any number of instantaneous configurations. Or really strings in this case, because we haven't really filtered those strings down to proper instantaneous configurations. Okay, so then we get this as the start and this as the end of the string, or of the pattern matching strings that look like this. And then in the middle, well, in the middle, you could sort of repeat the hash and the alpha any number of times. And so, well, let's just actually, for the sake of simplicity, place this hash here, and then just say that you could have an alpha and a hash any number of times, right? And so that'll work out. So we'll get alpha rex hash any number of times. Okay. And this is a regular expression to describe languages which satisfy condition C1. Okay, so clearly this is not enough for you to have a valid computation history string, because there's a lot of false positives. And so let's continue filtering this down through more and more conditions. So the second condition is going to be, well, for every alpha I in gamma union Q whole star, alpha I should contain exactly, exactly one state as a letter. It should start with a dash, and it should end with a blank. Okay, and so you could kind of use a regular expression for this. It's just sometimes it's difficult to write regular expressions where the condition is something like exactly one. And so instead, what we're going to do is we're just going to present an FA for this, right? So the FA for this, well, you might have your start state. So I'm writing the FA for just a single alpha I. Okay, but you can imagine, well, if it's alpha I star, you could just imagine looping back to the start state. Okay, so you have to start with the dash, and then you can have any number of letters over gamma, right? So let's just represent this with gamma, right? So this is an abusive notation, but I'm just saying this edge is labeled with all of the letters from gamma. And then at some point you have to have Q, right? You have to have a single Q in Q. And then after that, you can have more letters from gamma, and then finally you end with a blank. Okay, and then you can you can start this over, right? You can start this over, right? So then at some point, eventually you would get to the final hash, right? You would get to the final hash, and then you would get to the accept state, right? So this is an incomplete FA, but hopefully gives you the general idea of how you could design it. And so hopefully you agree that the language containing strings satisfying condition C2, that's also a regular language. Okay, so that's nice. The third condition has to do with what alpha 0 should be in particular. And so alpha 0 should be a starting instantaneous configuration. And so then it should be represented in a particular way, right? And so let's just write down the regular expression, which should represent alpha 0. So alpha 0 should have the following form. Where let's just use a regular expression straight up. So it will be the dash, then it'll be a very particular state, the start state, and then some string, right? Some string over gamma. So you could just, let me just abuse notation again and use gamma star, but this is just to mean, if gamma is A, B, the dash, and the blank, well, this is just that whole star. And then it should end with a blank. Okay. So I have a regular expression that represents alpha 0. And so what I'm doing is, if I have the language containing all the strings, which are, strings that kind of look like valid computation histories, but where in particular alpha 0 has this form, well, what I'm doing is I'm saying so far what I have is I have strings which satisfy conditions C1, C2, and C3, right? Because what I'm doing is I'm trying to create val comps using a conjunction, right? A conjunction of conditions. And so far, these three are my conditions. The fourth condition has to do with the specific description of alpha n. Okay? So alpha n must be a halting configuration. Alpha n must be a halting configuration. And so again, I'm going to slightly abuse notation and I'm going to say, well, then the regular expression for condition C4 would be something like, you would have a dash, then some string over gamma, then the accept state, then some string over gamma, then a blank. Or, so this is an or, the dash, some string over gamma, the reject state, not some reject state, there's only one, then gamma star again, then a blank. Okay. So the string, so this initial string alpha, right? So this initial string alpha should be the string that satisfies condition C1 and condition C2 and condition C3 and condition C4. Okay. So we're in pretty good shape of, describing a valid computation history. The real last piece that's missing is ensuring the consecutive alphas are respecting the rules of the transition function of M. Right? So how do we do that? So how do we do that in terms of writing down a condition? Well, it's going to be condition C5, which is going to say, for every I from 0 to n minus 1, the pairs of alphas, alpha I plus 1, they must follow the rules of the transition function of n. In other words, that alpha I in one step using the rules of M gets you to alpha I plus 1. Okay. So for example, maybe alpha I is some string U, then the letter A, a state Q, the letter B, and then some other string V. If this is alpha I, then, and in the transition function of M, I have that delta QB returns PBR. right? So this tells me that the Turing machine, when it's at state Q and it's reading a B, so exactly this situation, it should write a B and move right. So it should leave this B as is and move right. Well, then that must mean that in alpha I plus 1, I must have UA B PV. Okay, so this must be alpha I plus 1. So condition C5 is saying, well, this has to happen. This has to happen, and for every I. Okay. So in condition C1 to C4, we were very lucky. We had regular expressions, or FAs. So in other words, models of regular languages, which represented strings that satisfied those conditions. For C5, we're less lucky, and we can't even use models of context-free languages to model, in other words, accept or generate strings that follow this particular rule. Okay, and the reason for that, at a perhaps high level, is, well, to ensure that this is respected, right? To ensure that this is respected, let's say the PDA would need to scan this alpha I and memorize the U and the V, right? And then match it with the U and the V here. And it has to be an exact match, right? Because things have to be exactly consistent. But it turns out it's impossible for a PDA or a context-free grammar to accept or generate the language W, where W is even just, say, A or B whole star. Okay. So this is not context-free. And the reason why this is not context-free is, well, imagine you were using a stack. So you push the first half of the string onto the stack, right? So, if W is ABB, well, you push ABB onto the stack, so you have ABB. Well, now there's no way of you to recover W because you've pushed in last in, first out. So what you've done effectively is you've reversed a string, right? So now if you want to pop such that you match this W with this W, you're actually matching the reverse, right? And so that's why WW reverse is context-free, but WW is not. Right? And you could show this with the pumping lemma for context-free languages, and I had even given you what the pumping lemma string would be to show that. Okay. So that was in the lecture where we talked about the pumping lemma for context-free languages. Okay, so the sad news here is that we cannot model C5 even with a context-free grammar or a PDA. Right? But turns out that's not that big of a deal because remember what we're interested in Balcom's complement, right? We're interested in Balcom's complement because of this thing here, right? Because of this thing here, because we're doing not halting problem to all CF. All CF is asking whether L of G is equal to the set of all strings over the set of terminals. And so we care about not Balcom's equaling sigma star. So then we can infer Balcom's is equal to the empty set. And we care about not Balcom's equal to sigma delta star because that's how we're actually able to use the all-CF solver, because the all-CF solver has to do with checking if the language generated by the grammar G is equal to the set of all strings, not the empty set, the set of all strings. Okay. And so, bad news, but not so bad news, right? So then before we get to the complement, let's just write Balcom's out again. But now let's rewrite it as the conjunction of these 5 conditions, right? So Balcom's MX is a string in delta star where that string satisfies condition C1 and C2 and C3 and C4 and C5. So I'm writing it out because I got a comment during the actual lecture that, I should have written it out. So I'll do this here. And so, well, if you have a set where in set builder notation, you have a conjunction a conjunction of conditions, then you can split that as an intersection of those languages, each with one of those conditions, right? So you get alpha in delta star, where C1 is satisfied, and alpha in, wait, did I say delta star? Yeah, so alpha in delta star, where C2 is satisfied, and so on, right? So intersecting until alpha in delta star, so that C5 is satisfied. So then let's just rewrite this as L1 intersect L2, intersect L3, intersect L4, intersect L5. Okay. So let's now talk about the complement of Val-Comps. So if we talk about the complement of Val-Comps, well, if I have something which is an intersection of languages, languages are just sets. So if I apply the complement, to all of this, then I apply the complement to each of the sets, and I union them together, right? That's De Morgan's law. As long as I have a finite, well, in this case, because I have a finite number of languages, everything's okay, right? So I do L1 complement, L2 complement, well, union L3 complement, union L4 complement, union L5 complement. And so the reason why I was talking about, oh, like condition C3 can be modeled with a regular expression is because that tells me that these 4 languages are all regular, right? So these 4 languages are all regular, and this language is not even context-free. Okay? And so we can use closure properties for the regular bit. If I know that a language is regular, then I know that its complement is also regular, right? Remember, we showed this many lectures ago, where we said, well, just flip the accept and the not accept states in the DFA, right? And so then that means that L1 complement is regular all the way to L4 complement. And now we're taking regular languages and we're taking their union, right? So the union of regular languages, as long as it's finite, is regular. Meaning, I'm taking the union of a finite number of languages. If we deal with infinite unions, that's no longer actually true. Okay. And well, what's happened to L5 complement, right? That's the only other thing that we need to study. Well, it turns out that L5 complement is now context-free, amazingly, right? So that's not so obvious, but L5 complement is context-free. It is context-free, and so we have regular languages union a context-free language, and so then altogether we have that Val-Comps complement is context-free. And so if Val-Comps complement is context-free, that means that there is a CFG G which generates it, and so then I would be able to correctly say that I have a mapping reduction from the not halting problem to the all CF problem. So then all that's left to do is to show that L5 whole complement is context-free. Right. Okay, and this even actually showcases the fact that context-free languages are not closed under the complement, because if they were, then if this is truly context-free, then you complement that and get L5, and that should be context-free if you did have that closure property. But because it's not, well, that shows us that context-free languages are not closed under the complement. And so now what our goal will be to show, that L5 complement is context-free, right? So L5 complement meaning all of the strings which don't satisfy this condition C5, so meaning that there is a pair of consecutive alphas where this rule is broken. Okay, and so we're going to do that next.